Hello and welcome to the Instructor's Notes for Digitization Skills Session 1. I'm Ryan Muth, I'm the author of this lecture, and I'd like to go through it with you so that everybody can get a good idea of how to present this information. The objectives for digitization skills is mainly to talk about the foundational technologies at a very high level of the Internet of Things, right? So towards that end, we're going to talk about Internet infrastructure, the 4 pillars of digitization skills, data, processes, people, and things, and how we examine those aspects to develop applications and services for society. We want to talk about today, in this first session, how technology can change people's behavior, describe the function of sensors, and talk about ways that sensors collect information about people. The first thing I would ask the class is how people communicated before the internet, right? And I would expect a few minutes to get some answers from students and get some things like the examples I use are the telephone, the wired telephone. It's tied to the wall. You have to rely on fixed infrastructure to communicate with people. Similarly with snail mail, the physical mail system is how we would send messages back and forth. Even visual information communicated over broadcast, not even so much cable or anything like that, right? So these are all very slow, very limiting in technology, and in the case of television, it's a one-way communication medium. Even older than that, if we want to get really old school, we can talk about radio, again a one-way communication medium, and the telegraph, which was two-way but very slow and was actually the precursor to the telephone network. So the telephone network was laid down on top of the telegraph network, and then the cable network was laid down on top of that, as well as internet provider services now. So it's kind of like a chain of technology. We started out with telegraph wires, and now we have those same wires in some cases carrying broadband internet to rural areas. The next idea is, how has it changed? What do we have now that's replaced all of these things, right? So with the internet, how do people communicate? And for each of these items, there are some examples. Here I would ask the class, what has replaced all of these technologies? Say, starting with snail mail, and of course they would say email, right? We communicate using electronic mail, which is facilitated by the internet itself. Next, what has replaced television, right? Now we have cable television, we have smart TVs. They live on the internet. These things live on the internet, and we can now have bi-directional communication. We can request that a certain show be played at a certain time rather than having to wait for it to come around on the broadcast schedule. Radio has been replaced by satellite radio in some cases, or digital radio almost everywhere. Regular telephones have been replaced with the smartphone, which is a much more capable thing, and telephone calls are performed over the internet infrastructure. And the telegraph has basically been replaced by text messaging, right? The same kind of thing, short messages, all text, again, all facilitated by the internet, right? So we've been talking about the internet as this infrastructure that supports all of these technologies, but what is it really, right? I mean, we think about the internet, we connect to the internet, but as far as we know, once the phone company or the cable company or the network company comes to our house and hooks it up, we're on the internet and our computer just works with it, right? What I want the students to think about is, where is the internet? Right? We ask for a page, we ask for Google, we ask for Facebook, we ask for Instagram or something like that, but where does that come from, right? So where is the internet itself, right? So the idea here is that the internet is a global system of computer networks. That means these are computers hooked up together using some kind of network infrastructure, some type of a means of communication, and that allows them to send messages back and forth. The websites that we use are data that resides on a computer somewhere in the world, right? And it's really all over the place. The simplest version of the internet looks something like this. We start out with computers and browsers. This is your normal computer, your laptop, your desktop at home, the desktop on your machine in the classroom, something like that, and it makes a request over some kind of network connection. Usually it's Wi-Fi, that's the most common one, or it could be a wired network or something like that. And the first place that handles that request is what's called a router. And the router is what decides where a message should go. So if we're requesting information from Google, it doesn't go to the school's web server, it goes to the Google web servers or something like that. And this router provides the network connection, and the network of routers in the world provides the communication paths between your computer and the servers, right? So the servers are what provide information and services. Servers are just huge versions of computers. They're kind of like mainframes. They handle a lot of different users at the same time, and they're very specialized to particular tasks. In this case, serving the Google web page or providing the search functionality that Google provides. So these networks are usually connected to the rest of the world, the routers and the backbones, through wired physical connections. So this idea of the internet as a network of computers that trade messages back and forth can be really easily demonstrated by using this packet tracer activity. Now, as an instructor, if you go and click on the link on the presentation slides, it'll take you to a video where you set up the packet tracer software. The packet tracer software, a link to download the software is in the lesson plan notes, so you can go there to download it and get everything set up. This video shows you how to set it up and how to send a message back and forth. And really what we're talking about when you go and look at that is that a message is actually a physical thing. It's going to send a ping from one computer over here to this other computer, and this computer will respond, and the message has to bounce back and forth between them like a little piece of mail. And this is all happening digitally. It's a digital piece of information that gets sent back and forth. Now, this is a very simple representation of how machines talk to each other. The internet is way, way more complicated than that. This is a map of the total internet, and it's basically all of the connections between machines. So each one of these little clouds, at the end of every one of those lines is a computer. So there's all these computers connected together by some kind of routing system, and they communicate with the rest of the world through the internet backbone, which is a large network of high bandwidth connections that transfer information back and forth. So this is all color coded by where the servers are. So the red one that I was looking at is somewhere in Asia. The blue ones are North America. Pink ones are Latin America. When we talk about the internet, the way these things the way the computers send information back and forth is not just based on the web names, right? And computers actually don't understand the web names like Google.com or anything like that natively. So the idea here is that every computer on the network has what's called an IP address, and it's the Internet Protocol address. So if I go to Google.com, its actual address gets translated from a human readable name, Google.com, by what's called a domain name server into a server address, 172.217.0.132. So this is the address of a machine somewhere in the world, and this actually tells us all kinds of information. So the numbers, each of these groups of numbers, what we call a quartet, represents different pieces of information. The 172 and 217 are block numbers. So these are subnetworks of the entire internet, right? So these numbers all go up to 255, each one. So they range between 0 and 255. There are some special ones and things like that, but we won't get into that. But these first two numbers represent the block of internet addresses. So Google has bought addresses 172, 217, and it's bought the entire block. So it can pick any number for these two guys here, which gives it a huge number of computers that it could possibly use to communicate with the world. So you can tell who you're talking to by the number of these addresses, right? Just like I can tell where something is in the world by its street address or country code. Right? Same thing. Now, to find out this stuff, you can do this in a couple of ways. You can go to something like whois.com, or you can open up the command prompt in Windows. So if you hit the window key, the start menu, and you type CMD, it brings you to a command prompt. And this command prompt is an interface to the underlying operating system of Microsoft. And what we can do is we can do something like ping, and what ping does is the same thing that the packet tracer activity did. It sends a message out to a server. In this case, we'll do www.google.com, and it asks for a response, right? So if I do this, it gives me a bunch of responses, and it'll do this 4 times and then quit, and it actually changed the Google address into its machine address. In this case, it's 216.58.216.4. Now, this is a different block of machines, right? So Google has a lot of different addresses that it can use to represent the computers that it needs to talk to, right? So the real machine address, the address for the machines, which is always all numbers, is this IP address, and this is the human readable name. And that human readable name gets resolved by what's called a DNS server, a domain name server. Right, so this is the machine, a special machine that works for the internet that translates human readable names into server addresses that the rest of the internet can use to communicate. So what happens when we get a web page is when first we are requesting a web page. We'll type www.google.com into our laptop, and the first thing that happens is that laptop asks what's the machine address of google.com. So that goes through our home router, then through our ISP, it goes through the home router, which is connected to our internet service provider. That internet service provider says, if you're asking for a web address, you should go talk to this domain name server, right? And once it gets there, it gets translated into whatever the machine address is. And the domain name server sends that back to our home router as fast as it can, right? So now that our machine, our computer, has that machine address, it can request again, I want to know what is at this address. What can you give me at this address? And that goes, again, through our home router to the ISP, but this time, instead of going to the domain name server, the ISP says, oh, if you want information about something else, you should go to the internet backbone. Google is over there somewhere, right? So that goes through the internet backbone and then finally gets to Google. Google will process this request and send some data back in the form of the web page that we use to interface with Google. And that gets sent back all the way to our computer as quick as possible, and everything is hunky-dory, right? So this is a very high-level view of how web pages are requested from servers and how data is transferred between 2 points. And there's a lot of details that I'm leaving out here, but I want the students to get an idea of what actually happens when we're talking to things on the internet, right? So the next activity is about where websites that we use actually exist, right? So I would ask the question, what websites do you use the most? And do we know where that website lives in real life, right? Every website is a piece of data that lives on a server somewhere in the world, right? So let's look at an example. This is a really cool little tool. It's called Visual Traceroute. And the idea is that we can go to this web page here, and I can type in a remote address. In this case, it's google.com, and I want to do what's called a proxy trace. And what this will do will give me a chain of all of the servers that hop around to get me access to google.com. So if I do proxy trace, it'll ask for information, and then it'll give me a map of where my information has gone in order to actually request the Google page. There we go. So now it's showing me where the data went, right? It jumped from me here in Arizona out to Colorado, which is where my internet service provider is, then through servers in LA, then San Francisco, then all the way up to Washington. Now, we know that Google actually has a data center in outside of Seattle, so they have their servers there. And the numbers next to these things are how many hops. Usually there might be some little hops inside of a network, so if we zoom in here, yeah, everything's happening at the airport apparently, right? There's something outside of Denver that's handling the network connection there, right? But this is where my data had to go to get Google, right? Now, the next part of the activity is to see if you can find a website that travels the farthest. So I would let the students take a few minutes and start typing in websites and things like that, and see if who can get the farthest. If you notice in this piece of information down here in the corner, it had to travel about 2,000 miles, right? It bounced over here. It's definitely not the most efficient path, but this is what the internet does. It kind of ferries information from all over the world. So here in Arizona, we jumped up to Colorado and then around and around, right? My best one is one called Flipkart. And it's a Asian version of Amazon, basically, right? So this might take a few seconds to complete, but we should see a pretty epic path here in a second. All right, so it finished. It jumps to Colorado, my internet service provider. Then it jumps all the way across the world to India, then to Singapore, or China, actually. Yeah, Japan. Okay, here we go. So first, it jumps from me in Phoenix, then to Denver, then to Los Angeles, and this is where it hops on an intercontinental undersea internet cable. Literally, there's a cable that stretches across the sea, goes all the way across the world, all the way across the ocean. Here, it lands in India, then it jumps up to Japan, right? So this is a really long trip, almost 15,000 miles for this this web page, and I'll show you what Flipkart looks like. Right, if I type it in, boom, 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 it looks like a version of eBay, or not eBay, Amazon, right? So it's the same type of thing, and it just happens like that, right? Websites that are literally on the other side of the world are pulled to us in just a few hops over these massive networks, right? Which I think is super cool. Okay, so here's a little timer thing. This is a pretty cool thing. So if I click one more time, that 2 minutes block disappears, and you can sort of see a little green line growing here. And when that line gets all the way over here, it turns red like this, and sets off a little sound. So that's a nice little timer thing that's built into it. Let the students find a website that travels the farthest that they can find, and play with the tool to see how far somebody can get. I think that's a pretty neat thing to see this. Now, if I were doing this in class, I would then see if I can beat them. Hopefully Flipkart beats them. Maybe you can beat them some other way. And then we can start talking about how does the information travel across the ocean. I mentioned it in the slide before when I was talking about that big jump. But what is actually happening, it's not over satellite. Satellites are way too slow. We can't travel, like put it on a flash drive and ship it over there. It has to happen with a giant wire across the ocean. Right? We have these giant undersea cables that travel and across the entire ocean and carry tons of data, terabytes of data per second across the entire world. Right? So these cables are massive. There's an example, a couple of pictures of one here, and this is what it looks like to have a spool of one of these things. It's thousands and thousands of feet, many miles, 14,000 miles of cable to span the entire ocean. It's really incredible and super cool. And you can actually see a map of these cables at submarinecablemap.com, and you see where all of these links made. So we had one that went from, looked like Los Angeles, yep, right about there, and it went all the way over to India, which is probably this red one. So there are tons and tons of these cables physically laid down to connect the entire world. And you can see there's big bandwidth connections in between the United States and Asia over here, and between Europe over here. And it all depends on how internet is ferried, where that information is going to travel. So to bring it back to a high level discussion, we want to talk about what does the internet do for us, right? And here I would take a few seconds to try and get ideas from the class and really think about what is it that the internet does for it at a high level, right? It lets us communicate, but what kinds of communication are happening, right? So the first one that I would talk about is it allows us to communicate with each other, what we call P2P, or person to person, right? It allows us to send email, we can send text messages, send videos, we can do live video chats, we can do all kinds of stuff, right? And the examples of this, I would give a couple examples. The typical ones are email and text messaging, that kind of stuff. Then the next type is it lets machines communicate with each other, right? So we can do things like we can have our weather reporting information. We can have traffic information. These things can talk to each other. Machines can report how many cars are traveling on a particular highway. If it's a whole lot of them and they're going very slowly, then that can be communicated to the road signs, and they can actually display that there's traffic ahead or there's some kind of issue. The weather reporting system is totally automated from one end to another. Right? The weather stations around the world report information to a big database, and that's read by the National Weather Service, and they do a calculation on how that's going to affect the overall weather patterns. They do predictions, and those predictions get posted online. That is all happening without human intervention. So these machines are talking with each other. Now, where the real power comes in, and where sort of the frontier of development is allowing machines to communicate directly with us, allowing machines to do work for us. And this is what the Internet of Things, the Internet of Everything, and these digitization skills are all about, right? So the next activity is kind of a side thing, but it's to sort of frame what's going to happen next. So the idea is, what do we want the Internet of Machines to do for us? What do we want Internet machines to do? And the idea here is the students to make a bug list. And this is a entrepreneurship mindset activity where basically we want the students to make a list of the things that bug them. Right? What are the problems that they encounter in their daily life? Think over the day, think over the week. What has made you angry? What's made you frustrated? And is there a way that we can solve these things? Right? So let's not think about how to solve them. Just what is the problem? What is the list of problems that we have now? How do we and are they and let's write down the ones that we think we could possibly use, even if they're totally off the wall. You know, it's hot outside, or there's tons of traffic, or something like that, right? Things that may not have an idea of what the solution is now. Let's just talk about the problems, right? So once the time is up for that one, just tell them we'll save these, we'll use them later, and we will in a couple of sections, right? So the next bit is to talk about what the 4 pillars of digitization skills are. The first one is people, so we'll talk about the central tenet here is we're designing things for people. So we want to talk about how we can work with people, how people can behave, how people's behavior changes due to technology. Then the next is data, and data is all about gathering information about the world. It's gathering information about people, it's gathering information for people, it's gathering information about our environment. And data is different from information in that it's raw, right? It's just strict measurements. The next one is to take that data and perform a process on it, right? We want to process the data into something that's more useful. We take this raw data and we turn it into human readable information or trends or suggestions on how to do things. And the last one is the things. We want to incorporate all of these pieces into the things that are around us, things that aren't normally what we would call dumb appliances or dumb devices. We want to make them smart. We want a smart home. We want a smart fridge. We want a smartphone, things like that. So talking first about the people part, right? Can information change how people behave? And this I would pose to the class. Can they think of any examples where new information from some kind of source has changed has changed how we behave? What if we know if there's traffic on the way to work or to wherever on the way to school? What would you do differently? If you know it's going to rain in an hour, how would that change your plans on the weekend? If you know the next season of your favorite show just dropped on Netflix, what is that going to do for you, right? How is that going to change your day, right? And of course, all of these things change how we behave, right? And these are all driven by information sources in the world. So the idea here is to tie it back to how can we change people's behavior for the good to enable new technologies and things like that, right? And the truth is that businesses and organizations use data all the time to improve their customer service. For example, rewards cards are a fantastic boon to businesses. They look at what you buy and give you coupons or give you suggestions. They even send you personalized recipes. And what this does is it promotes your behavior to buying more. If you get a coupon for something and a recipe on how to use it, you might buy the extra stuff that gets associated with it. So they get more revenue, they get more people into the store, you're more likely to buy things. Ad services. These are things that track what you're looking at, and they show you targeted advertisements. Right here, we're looking at the iPhone 4, or a report on the iPhone 4, and you can see that there are technology-related ads that are tied to that article, right? They're focused on audiobooks. How are you going to use the smartphone? The car down at the bottom is smartphone enabled. It's about on-topic stuff and how to sell services and things like that. So this is how businesses tie in what they're sensing, which is information that you give them as a consumer, and to the things that you use, right? To try to sell you things, right? And it not only comes down to that. So let's talk about an information inventory, right? So here in this part, I would ask the students, think of a company or website that you interact with daily, right? It might be Netflix, it might be Amazon, it might be someplace you read news, Instagram, Snapchat, whatever you want, right? Now, what information do these companies gather about you? What do you give them, right? And take some answers from the class. Common things might be obviously your name, your address, your email address, your phone information, right? When you install an app, it asks you for permission to see your contacts and your pictures and all kinds of stuff like that. And this is all information that the company now has available to them. And when you do something, say on Instagram, you post a picture, that picture is now available to them. Plus all of the stuff that you add to it, like who you're connected to, who's favoriting your picture, who is commenting on your picture. All of that information is being gathered. Now, what could companies do with that information to change your behavior? Right? It could serve you specific ads that are targeted to what you and your friends like. If it sees that you're, photographing your food a lot, maybe it'll give you ads for local restaurants. If it sees that you're, in a particular location, it might show you where shopping is available or something like that. They're trying to influence your behavior to bring you into the door to get you to buy stuff. Right? And that's most of the time what they do. But it can be even more subtle than that. The next pillar is data. And what data is raw measurements about the world, right? And computers are doing this, right? So where does data come from? How do we get it? And it can come from several sources. One is manual measurement. You go and take a ruler and you measure the size of stuff. Or you take a thermometer outside and see that it's 85 degrees. Or you go and literally count how many cars are crossing the road, stuff like that. But where the power really comes in is sensors. Sensors are devices that convert physical changes into electrical changes that computers can read. And there's all kinds of different sensors. Some are digital, and these are something that measure the presence or absence of something, right? It's, is the door closed? Is there a car waiting at the stoplight? Is the button pressed on the computer or keyboard or something like that? These are very simple sensors. They give you a yes or no about something, right? Analog sensors are a little bit more nuanced. They tell you how much of something is there. Is it bright? Is it dark? Is it super bright sunlight? Is it indoor light? Is it midnight dark? Is it just a little dim? Right, that's kind of thing. So, or it could be temperature. It could be, how warm is it? It's really hot, it's medium hot, it's very comfortable, chilly, cold, freezing, right? That kind of thing. Or it could be something like distance. That's what this weird one down here at the bottom is. This one tells us how far away something is. Not just where something is or if there's something in front of it, but how far away it is. And these are analog sensors. So the next activity, this page, goes into how to do a little example for implementing these things. So you can go to google.gl and download the Arduino sketches, the examples that we're going to use, and you'll also need to install the Arduino software. There's links to the software in the lesson plan, so you can go and check those out as you need it. And then I'm going to walk you through how to get this this whole thing started up. The first one is this first circuit here. So the physical component, you're going to get an Arduino. It's going to be a red board, probably looks like this, and a breadboard, which is this grid-like thing on the back here. And what it is, what this breadboard is a bunch of little holes, and each of these holes are electrically connected to each other. So all of these 5 right here on row 10, you see there's a row 10 there, all of these 5 are connected to each other, but they're not connected this way, right? So this row is connected to each other, but the columns are not connected. However, on the outside here, you've got these rows that are connected in groups of 5, and they've got this red and blue lines. These are all connected together like this, right? So they're all connected together in this direction, but they're not connected together in this direction. So it's a little confusing, but pretty simple to get started. And what these are basically built-in wires. I can plug anything I plug into this one, and if I share it with anything else in these other holes, gets shared there. So you can see example here, this yellow wire is connected to this row, which is highlighted green, which is connected to this leg of the switch, which is also connected to this resistor, which is connected to ground, right? So that's a path, one circuit path for this little electrical system, right? Another one is this leg of the switch. All of these guys are connected together to this red wire, right? So here in this case, the way we're looking at it, the columns matter, and you can rotate it, and it's a little confusing, but the idea is these groups of 5 are all connected together. And then in this screen over here, this is the Arduino software, and there's a couple of things to note. The sketches that are available can just be opened directly into it. So once you download that zip file from the website, you can hook this up and get it going. And then all you have to do is open Button Sketch from inside the software and hit the upload button, and it'll upload it to the board. When it says done uploading, it should be ready to go. And we'll do a little demo of that right now. Okay, so here we've got the circuit built. And what we're going to do is we're going to look at it each piece by piece, right? So here in the on the breadboard, you can see that it's not as pretty. It's not as pretty as the diagram, but it pretty much reflects it completely. So here I've got the Arduino, the red board, and I've got it connected to 5 volts over here to the positive rail on the breadboard. Then I've got the ground, this ground right here, connected to the negative rail on the breadboard, and both of those, negative rail to this little guy here, and this is a resistor. It's really kind of hard to see, but he's a little tiny dude, and he's got 2 dark stripes. Now there are 2 kinds of resistors in the kit. There is one with 1 dark stripe and one with 2 dark stripes. It doesn't really matter which one you use as long as you use one. And the big caveat here is making sure that all of the things that are connected together, in this case, here I'm going to move this a little bit so you can see, all the things that are connected together are on the same row. So here you can see I've got my resistor leg is on the same row as that ground resistor. So those are all connected together. Then there's a couple of gaps, and the other leg of the resistor, moving again, so hopefully you can see a little bit better, the other leg of the resistor inside here is on the same row as the leg of the switch. And now notice my switch looks a little bit different, but it should behave exactly the same. You want to pay attention to what leg, what hole, what row the switch is sitting in, right? Same thing for the red wire, and then the yellow wire, which is actually my sensor wire. That yellow wire goes over here to pin number 2 on the Arduino, and you can see the labels here on the rows. Same thing on there's labels on the inside next to the power ones. Okay, so let's switch over to the Arduino part. Another thing that's really important is when you're building this circuit, do not have this plugged in, right? So there's a USB port over here, which we're going to hook up here in a second. If we scoot this over a little bit, you can see there's a USB port, and we're going to connect this. Now, Now that the circuit is built, you want to make sure that there are no problems or anything like that, that everything is checked out. As an instructor, I would build it first to know what's going on and all that kind of stuff. And before students plug it in, go through and check and make sure everything is put together correctly before you plug it in. Otherwise, you run the risk of burning out the board or the components. You'll never start a fire. There's not enough current. There's not enough power in these things to really do any real damage. But it might not work. That's the worst thing that will happen. Right. So once the circuit is built and it's been checked out, you can go ahead and plug it in. And you'll see a little light turn on, and this is the everything's hunky-dory light, right? And it says, I'm ready to receive a program. So let's go and plug in the other end to the computer. That's when this all turns on. You'll see the little on light turns on. And we want to make sure that everything works, and we're going to upload a program. So going back over to the computer, inside of the Arduino environment, this is the Arduino started up. We're going to go to File, then Open, and we're going to navigate to wherever the thing was unzipped. So I'm going to go to the button sketch folder. I'm going to open the buttonsketch.ino. I open that up. The other one, it opens up a new window, and we can see some stuff in here, right? And the behavior is pretty simple. So here is the setup. This is what drives the initialization. So this function, it runs once, and it does things like set up the inputs and set up the outputs. So pin 2, the one that we plug the yellow wire into, that's an input, and pin 13, which is connected to the blue LED on the board, that is our output. So we're going to do something with that. And there's also some serial setup stuff here that is a little more complicated. So the idea is we're going to output whatever is on pin 2, and that's what the digital read function does for us. We're also going to do if. There's an if statement here, so it says if digital read 2 is high, if the button is pressed, set digital write pin 13 to high, which turns on the LED. So basically what we're saying is if the button is pressed, turn on the LED. Otherwise, if the button is not pressed, turn off the LED. And then we wait for a second. So now that I've explained the software, the first thing we want to do is go to Board and make sure Arduino Genuino Uno is selected, which it is, and then go to Port. When you plug in your board, it's going to tell you one of several ports. It's going to tell you a COM number, right? Or if it doesn't, you'll have a list here. It's usually the one on the bottom is the one to pick. Try if you've got more than one, what you can do is you can unplug the board, and whichever one goes away, that's the one you want to pick when you plug it back in. So mine is COM6, so go ahead and pick that. Now that I've got my Arduino all set up, I've chosen the right board and I've chosen the right port. I just have to hit the upload button, which will compile the sketch, and if there's no errors, these red and green LEDs should go, or these yellow and red LEDs should go crazy, right? And then the RX light should blink really fast like this. And what's actually happening is that the board is now running the program that we just put into the Arduino, or into the Arduino environment. So let's look at what's actually happening here. So it actually follows the process of the program. So when I press the button, and the LED goes, and the line goes high, the input line goes high, LED 13 turns on. And when I release it, it goes low and turns it off. High, low, high, low. Isn't that awesome, right? Now we can actually see this in the software too. If we go back to the Arduino environment and look in the serial monitor, click the serial monitor. If it gives you a weird error about COM port busy, just try it again. That's Windows 10 for you. And now, if we're looking at this, we see a bunch of zeros here, and this is actually the state of the button. So if I go ahead and press the button again, it turns to ones. I release it, it turns to zeros, ones, zeros, ones, zeros. And this is the foundation of digital information, right? It's whether or not there's the presence or absence of electricity which causes all this stuff to happen. And this is really what's going on, right? So the board is making a very simple decision, which is, it does it very, very quickly. It does thousands of them a second, which causes a lot of behaviors. And really, this is the power of computers. It's very simple decisions done thousands of times a second, which builds up to very complex behavior, everything that we do with computers. And this is the simplest form of sensing. We're sensing the presence or absence of something. In this case, the presence or absence of my finger pressing down on this little button. But it can be the presence or absence of a door being closed, or it can be whether a car is waiting at a stoplight, or any kind of stuff like that. Right? So let's move on to the next example, which we'll use an analog sensor. So the next example uses an analog sensor that senses the rotation of a knob. Right? So this sensor might come in a bunch of different shapes depending on your kit. Most likely it's going to be a little blue sensor, or it might be a big gray one like we have shown here. So with this one, it's just 3 more wires. We can keep the same circuit that we had before. A black wire, a green wire over here to the analog input section, and a red wire over to the power. So let's look at what that looks like. Okay, so here we have the analog input circuit. We've got a little knob over here. Mine happens to be blue. We've got a green wire going over to analog 0, a black wire going to the ground rail. We've got a red wire going over to the power rail, and they're all on respective pins that are connected to the little blue variable resistor, this little blue knob here, right? So remember again, when you're building a circuit, don't plug in the Arduino until you've checked all the circuits. Don't change things while there's electrical power. That can hurt the components and things like that, but it'll never hurt you. There's no safety issues here. Just make sure that things aren't plugged in when you're working on them. So now we can go ahead and plug it in. And we get the little blinky light of readiness, and we're going to go back over to the Arduino environment, and we're going to open up a different sketch. So I'm going to go to open. I'm going to go up one to the knob sketch, knobsketch.ino, and open that one up. And this one is very similar. You'll see that it's very similar to the regular Arduino sketch, to the last one, the button sketch, except we're using a different input. We're using analog read from A0, analog input 0, and we're making a different kind of decision. So instead of it being high or low, it's about a number, right? Because this analog sensor, this knob, is going to give us a position as a number between 0 and 1024. So here we're saying if the position is greater than 512, turn on the LED. If it's less than that, it'll do this part, right? So if we go ahead and upload this, we should see the little blinky lights turn on. There we go. And I'm going to use a screwdriver here because my hand would confuse it, but you can just use your hand to turn the knob so you can see, or I just want to, just for clarity, I wanted you to see this without my hand being in the way. So as I turn the knob, watch the LED over here. As I turn the knob, oh, it turned off. Right as I went past the halfway point, it turned off. If I go back the other way, it turned on, off. I can turn it all the way down, turn it all the way up, the LED goes on, right? So there's a little halfway point in there, something like that. Now where the power really comes in is if we go back over to the Arduino sketch, you'll see we're outputting to the serial terminal the value that we get back from the sensor. So when we start reading this thing, you can see the number that corresponds to the position. So when I turn it all the way down with my screwdriver, it goes all the way down to 0. When I turn it all the way up, slowly, you don't have to go slow, you can go as fast as you want, but you can see right as I hit 512, the LED goes off. And then I turn it back up again, it turns on, and goes all the way up to 1024, right? So this is a sensor that's giving us back a level of something. How much is the knob turned? Not whether the knob is turned all the way or not, but how much the knob is turned. And we can set thresholds. That's what this number here is, this 512 is, to define behaviors that should happen. Now I could have a bunch of different behaviors. I could say if it's between 0 and 300, do one thing. If it's between 301 and 500 do something else, and so on and so forth. So I could do all kinds of stuff based on what number the knob is giving me back, right? And this is what an analog sensor is. And between these two types of sensors, we can capture all kinds of information about the environment. So the next activity is the quantified self activity. And there's a worksheet included in the course materials that's based around this, right? And the idea here is to get the students to think about, what would you like to know about yourself? What would you like to measure about yourself? Let's look at the worksheet really quick. So in the quantified self worksheet, we have this outline of a person. And the idea is to illustrate the things that you would like to measure about yourself. For example, use a heart rate monitor to measure the amount of exercise you do during the day. And to help with this, on the back of the sheet, there's all these different kinds of sensors. So we have the heart rate, electrocardiogram, what type of sensor it is, what does it measure exactly, and what are its limitations, right? And the idea is we want to start trying to tie this back to their bug list. We have a problem that they want to solve about their life. How do we start to solve it? And the first step is, what can we measure? What can we do to see how our problem relates to the real world, and what kind of data can we gather about it, right? So that's the end of session 1. Here we would end, take a break if you're doing both of them in the same day, and then come back to session 2. All right, let's start session 2. In session 2, we want to talk about the other 2 pillars and start bringing this all together. So we're going to talk about how processes provide services to people, try to identify opportunities for digitization in your life, and we want to give you some of the skills that would lead to implementing a simple internet-connected digitization system, right? So, again, reviewing the digitization skills, first one is always focused on people. We want our devices, we want our services to be people-centric. We want to help people do something. Next, we want to collect some data in order to drive these processes that allow us to extract information from systems, make decisions, and take actions. Then we want to wrap all of this, we want to put all of our solution into the things that are around us, right? So the first step, the next step that we're going to be talking about is processes. Now, processes are what turn measurements and information into actions, right? Turn measurements into information and actions. Now, we basically start with a whole bunch of data, and we're going to throw away most of this data because it's noisy or weird or something like that. But as the processes work on it, they're going to turn it into decision making, which then turns into actions. We want to do something with our data. Now, there's a difference between measurements, which is data, and information. Information is something that means something, right? Data is usually raw. It's some kind of direct measurement. It may be noisy, or it might be too small of a scale, too fine, something like that. Information is actionable. It tells you something for sure about something that you're looking at, right? It's something that means something to whatever problem you're trying to solve. And that's a little fuzzy, but I think some examples will help, right? So the first one, this is a picture as a computer sees it, right? So each one of these little squares contains a number. What do these numbers mean, right? We don't really know just looking at it, right? We got a pretty high range. There's a 0 here, there's a 254 there, stuff like that. But what this number really means, who knows, right? So let's impose a first layer of meaning on it, right? Let's say that 0, each one of these, let's say that each one of these cells, each one of these little squares represents the brightness of one of these pixels, right? So 0 brightness will be very dark, and 254 brightness will be very light, right? So we've got white here and black there. So let's transform that. Awesome. Now we've got something, right? We've got something that's more like a picture. We've got an idea, we've got the first idea of what this might be. Now, this is a little bit, we've got more meaning, but we still can't recognize what this is a picture of. So maybe we need to zoom out a little bit. We need to collect more data to see what the context of this is, right? So let's zoom out a little bit. Can we decide now? Do you have an idea? Still a little fuzzy. right? So let's get some more data. Any better ideas? We're starting to see things, right? This kind of looks like a person, maybe. There's some arms, something like that. Maybe this is a person too, right? Zoom out all the way. Oh, it's a dude on a bicycle in front of a van, right? Even more context gives us a lot more information, right? So just that raw data, those numbers in a grid, don't tell us much, right? But giving it context, giving it meaning, turns it into information, right? If I were to say, circle all of the people in this picture, I would have to take all of that data and turn it into patterns that represent people, right? Right off the bat, I see 4 people. There's one here, one there, and one right here up close, right? So there's a lot more to processing than just gathering data. We need to turn that data into meaning, right? Here's another example, right? Here's a bunch of data, right? I've got some dates and I've got some numbers, but what does this really mean, right? Well, I'll tell you, this is my track record of how well I'm achieving my most common New Year's Eve goal, right? This is actually my weight over the last few months, right? And you can see it varies a lot. I start out pretty high and I'm a little bit low. Now, have I lost weight? If I look at my first one here on the 27th and I look at my next one, it doesn't really seem like it, right? Especially since there's a spike at 250 here in the middle. So I've gained weight, I've lost weight. There's some pretty big fluctuations here, right? So looking at this, it's kind of hard to see trends. So let's transform the data. Let's give it some extra meaning. Let's graph it, right? So if I graph it, it looks like this. And we see some kind of the same trends. I start at a little bit above 247. I end at just on 246. Doesn't look like I've lost weight, right? So let's do some more processing. Let's take a running average and actually put a trend line on it, right? So if I add a trend line, I can see that, yeah, I'm very slowly, which is healthy, losing weight slowly but surely over time, right? This is a great example of extracting meaning. Am I losing weight, yes or no, from raw data by adding different kinds of processing to it, right? Now the next step is, now that we know something, what do we do with it, right? If we have some knowledge, what good is it, right? And I'll tell you, it's to take an action. We want to do something with the knowledge. We want to take some kind of action. And all actions come down to a decision. If we know something, if something is true, then do something about it, right? So all of our knowledge, our inputs, our data, our information comes in here, and the outputs, what we're going to do with that information, comes in here, right? And this if-then statement is the foundation of decision making. This is how we tell computers, we give them a rule, if something happens, then do something about it, and the computers just follow this rule. They make this decision and take an action, and they do it for us, right? So let's look at some examples, right? For each of these examples, I would like you to tell me, what's the problem we're trying to solve, what can we measure, and what can we do about it, right? Let's write an if-then statement. For example, GPS and traffic detection, right? What's the problem we're trying to solve? Here I would ask the class, what's the problem, get some ideas, stuff like that. We want to detect traffic, right? What can we measure? Maybe we can measure the number of cars in a particular area, or all of the speeds of these cars. We want to gather data from a lot of stuff, right? Now let's write an if-then statement, right? Something like that. We want to write on the board and get some ideas from the class. And you should take a few minutes to do each of these examples. But the idea is to try to get them to come up with an if-then statement. A possible if-then statement might be something like, if the cars around me or ahead of me by a mile are going less than 10 miles an hour under the speed limit, then I should probably try to redirect my route, right? I should go around it, see if there's any extra options. That's a simple if-then statement. Let's go to the next one. Recommended movies and products. What is the problem we're trying to solve? I'm bored and I want to watch movies. what can we measure? Things I've looked at in the past. What do I like typically? Do I like science fiction? Do I like westerns? Do I like rom-coms? Stuff like that. So what's the if-then statement, right? If I've liked sci-fi movies in the past, recommend sci-fi movies I haven't watched. Pretty simple, right? It gets way more complicated when you start to consider, maybe I want to watch a good sci-fi movie and not a bad sci-fi movie, right? I don't want to watch, Sharknado. Maybe I do want to watch Sharknado. That's pretty awesome. But, it's a very poor movie. It's almost so bad it's good, right? Stuff like that. So it's hard to make these decisions. The if-thens can get very, very complicated. But again, at its core, it's the foundation of decision making, right? And continue this with home automation. What can we measure? What problem are we trying to solve? Let's write a home automation if-then statement, right? So the next bit is the bug list and the process design, right? We want to pick a bug from our list or come up with a new bug. So we're going to use the same list that we used before and go through the same process. What can we measure? What data can we use to help solve the problem? Maybe use the data collection examples from the quantified self example, right? Then let's determine what action should we take, and we'll write an if-then statement. And I give the students about 5 minutes to do this so that they come up with all their plans and then have them share and talk about how they could improve it, different things like that, right? Next, we want to talk about things, right? So for this first one, what I would like people to do is talk about the everyday things that they get, right? So the idea here is I want them to do a flash task very quickly, make a thing list, right? In the 1 minute that I give you, make a list of every human-made thing you've interacted with today. And I want them to be really, really broad thinking. So not just electronics, but think about all of the things around them that are made by people, right? And try to make as big of a list as they possibly can, right? So the longest list before time stops wins, and what they win is respect. There's always somebody that asks. But after the time expires, ask them to count up their items and find out who has the longest list and have that person list them off. And start a little quick conversation about things that might have been surprising, right? I would write down things like the road surface that I drove in on today, or the windows, the building, the box of Kleenex that are here on my desk next to the computer, or the water bottle that I'm drinking coffee out of, or anything like that, right? These things are all made around us, right? And each one has the potential to be digitized to help people solve problems. Some are better ideas than others, but they all have the potential to collect information, right? So when we connect a thing, say we want to connect my coffee maker, I want to make my coffee maker smart. Some of the first things we have to do is add those sensors. We have to be ready to collect data through the use of sensors. Sensors need some kind of computer, a controller, and the controller is, like our little Arduino, usually something that's networked. It's connected to the internet in some way. Then I have to have actuators. I have to have the controller be able to control or actuate whatever it is that the system is that we're operating on. Also, I have to do the programming. I have to define what decisions it's going to make. So if the device runs out of coffee, if it senses that it's run out of coffee, then I want to send a text to order more. Or I maybe I'm, my smartphone goes off, my alarm goes off. If my alarm goes off, then maybe trigger the system to start making coffee. That's something that'll make its own action, right? So let's think about smarter things. I want you to pick one thing. I want the students to pick one thing from the everyday things list. And let's answer the pillar questions, right? First, what is the problem in your life that we can solve with this thing, right? What data can we collect from it? What kind of sensor would we need? Again, referencing the quantified self table where we have all those different kind of sensors. And then let's think about what is the behavior. Describe these if-then statements, right? So give them about 5 minutes to do this, and then we're going to do one of two different kinds of activities, right? This one we call the Shark Tank. And the idea here is in teams of 2, take a few minutes to prepare an elevator speech. Now, an elevator speech is a really quick speech, usually about 90 seconds, that is what you would give if you ran into the CEO of a huge company in an elevator. You only have a few floors to pitch your idea to him and get him to give you money, so try to convince people to buy the product, right? So answer, what is the product problem, what's your product, and why should people buy it, right? You want to finish in under 90 seconds. So break up into little teams and do this. Teams should be randomly chosen, right? Either take volunteers or randomly pick little teams and allow each team to give their speech. I would do 2 or 3 teams and then have the class vote on who gets the most investment, right? Every person in the class has $100. How much would you invest in each team? You must invest it all, right? So either you give all of it to one team or you split it between them. But the idea here is why. If you only invest a little bit, what could they improve? If you invest a lot, what did you like? Right? So give them some feedback and spend a lot of time working this out, because this is about entrepreneurship. It's about solving problems. It's about bringing all of the things that we've learned together to try and solve problems in people's lives, right? At the end, after that, I've also got a home automation activity, but this is currently broken, so don't worry about that. The state of the art. So now bringing this all together, let's look at some things that are successful. One of them is the Amazon Echo. Now this is a device that sits in your home and it listens for its name. It's usually called Echo or Amazon or Alexa or something like that. And you can give it commands. You can have it play music, or you can have it email people or text people or order stuff from Amazon or set reminders, all kinds of stuff. It's something that lives in your house and is an interface to the internet over voice, right? Hands-free. Another one is the Nest, and this is a thermostat, again, that lives in your house, and it, rather than just controlling the temperature of your house, it learns your usage pattern. So it can figure out, you come home every day at 5 and turn the temperature down to 64 degrees. Right, that's really chilly, but that sounds awesome right now since it's starting to warm up in Arizona. So it can learn that pattern so that when you come home, it's already set itself to 64 degrees, right? Which is pretty cool. This is connected to the internet, so you can control it from your smartphone, you can control it from a web interface, all kinds of great stuff. Tesla is a great example of a vehicle that is internet connected. It gets you might get in your car one day and find that it has downloaded a new interface. It has gotten a firmware upgrade or something like that, and people actually did wake up one morning a few weeks ago to see that their car now had an autonomous mode. It could drive itself without crashing into people, which is both scary and awesome. Another one is the Samsung Smart Fridge. This is a fridge that basically has a tablet computer and a bunch of sensors built in. The idea is that it can keep track of the inventory, what you have in your fridge, and suggest recipes that you could make. Or if you run out of something, it can automatically email you a shopping list or something like that. Right? Another one is the Fitbit. It measures your heart rate, your activity levels, how much you move, all kinds of good stuff like that. Right, so these are all things that people are doing, and you should start to think about what can you do to solve different kind of problems. And the last few slides here are just a recap. We talked about the internet structure, how information gets from the outside world into your own computer. We talked about the digitization skills, how we are people focused when we design products, how we gather data, turn that into information and actions with processes, and we wrap this all up by putting it inside of things, right? Now, if you want to learn more, you can direct the students to the Cisco Network Academy. They go into a lot more depth. It's probably a couple weeks of work to get into this, and they have a lot of information on how to apply and build applications that work with across the internet and things like this. So this has been a high-level summary of the Cisco Network Academy, and if you have any questions, you can email me at ryanmuth, ryan.muth, M-E-U-T-H, at asu.edu, and I can give you any suggestions or information that you'd like. Thank you very much.